The VNC, you mean? Or I have the address still. Okay. There we go. Yeah. I haven't found any hotkey to disable VNC as I'm sort of, oh, sorry, sitting here being pretty. Okay. Okay. I've read up a little bit on the registers and what they mean.
Okay, hello guys. So yeah, people were actually asking right before I started streaming if I were going to stream tonight or not. And yeah, I can recognize the names already. Hello C8, hello Medusic. So Metal Snake is here. We're sharing my desktop. We're both on audio. Obviously, you might probably heard him too. So what we're doing tonight, you're probably aware, just to say it again, we're doing a very small educational operating system kernel. Like, I should really say kernel because even kernel isn't appropriate for what it is. It's like a very small monolithic operating system. A kernel would imply a shell, something around it. There is nothing around this one. It's going to be on x86, no virtual memory, 32 bits. Oh wait, I forgot to do a couple of things. I forgot to actually write what I was doing tonight. Sorry guys. Let's call it a kernel since that's the title too. Okay, that will be enough. All right, so the first thing we need to do is probably add Metal Snake to the list of users who can display screens like graphical or Windows really, because this is my session and we have a multi-user setup. We have created a very small Git repository which you can actually check on GitHub. It currently has nothing. Like, there is a small hello world file. There is a make file that is like the most basic thing you can find, and a README that just says what this thing is about. So it's really the beginning. We should establish a roadmap first, and ideally we should do what's most interesting for the viewers first, because some of them just can't stay until midnight or so. Salut Roberto. So the build system, we'll only have a single make file. Let's not make things complicated. But I was wondering what kind of features we should have. Like, for example, are you guys interested in automatic dependency tracking? Do you think that's a thing students should know about in an educational project? That includes you, Metal Snake, by the way.
Yeah. So automatic dependency checking, as in what files are dependent upon for the uh, for the project?
Mostly headers.
Okay.
When you change a header, you want all the files that use this header, directly or indirectly, to be rebuilt.
Mm-hmm.
And you want the list of headers to be generated by some tool, not to be maintained manually, because it's too like there's gonna be mistakes if it's not automatic. So, like guys, is that a thing you want to see, or should we switch directly to something else, like to actually booting, and I'll make the makefile later?
Personally, I don't have a lot of experience with Makefiles, but that is also something you could look up.
That's why I'm asking.
I'd say it's not really in the interest of the exploring how the kernel works.
Okay. Bootloader, not really. We're gonna use Grub. We're gonna use Grub. So the same kind of setup I have on X15, but the code will just be simpler. Like the reason we're not going to write a bootloader now, at least, I think I remember Metal Snake talking about writing one, but that will be his project. Um, a bootloader isn't that interesting, really. Um, and it changes a lot between architectures and machines. Whereas the basic concepts like context switching and scheduling are really independent of the hardware mostly. I'm okay with everything. Okay, why not? Um, I guess we should start with booting. Okay. I'm sorry. Okay, so we still need a makefile to build things, to get things started, because we want to actually test what we're doing the best we can. So we'll make like a makefile that just rebuilds everything all the time. Um, yeah, something like this. At the beginning, at least. Since we'll only have a couple of files, it won't be long anyway. Um, and we should start with the linker script. So, guys, are you like to what amount like of detail, for example, would a student be interested in a linker script? Uh, does linker script does the expression actually talk to you? Do you know what it is? Do you understand what it's for?
What I think it is, it's you link the compiled objects together.
So that's the linker, but the linker script.
Oh, right. Sorry. That's for allocating the stack and heaps and all that jazz.
Yeah, when you have them, because they could be outside the kernel, and on advanced kernels they usually are. It's mostly for what's in the program. So text, the code, data, BSS, which is uninitialized data, and any other sections that are not standard that you might want to add. So here, um, we're not going to make things difficult, right? It's a minimized kernel, it's educational. So we want a very simple linker script, but we still need one, because if we don't use one, the default is going to be used instead, and the default is meant for a hosted environment in virtual memory. So that's really not what we want. Um, okay, I think it's not really important to make the code portable either. It's for x86, it won't change, it makes things simpler, I think, right? So let's start with this. We're going to write the boot code, like the very first assembly instructions, and then we're going to write the linker script. Okay. Now, one thing I'm wondering is when you should code. Like, what I'd like to do is do it in small steps. Um, I don't think you can handle the linker script right away, but booting itself is probably something you could do. Like it's simple assembly. It's not complicated. You might be confused at the beginning, but with the right pointers, you should pick it up quite quickly. Okay? Is that okay with you?
Sounds good. Sure.
Okay.
I do not have a lot of experience with assembly, though.
Yeah, that's okay. That's great, actually. So, main is going to be the point we want to reach. Now, this is not hosted, so we don't have stdlib, and we don't have a printf, so for now we won't have any output, guys, okay? No output. We'll have to choose what console we use later, and depending on what kind of features we want, like do we want input, in which case the keyboard is a nightmare, or just output, in which case outputting to VGA is quite easy. So we'll have to make a choice. But for now, let's just make an infinite loop. So yeah, the makefile works. Yeah, we don't have exit success. And let's say void returns nothing. Oh, that's right. So one thing that's important when you start coding that kind of project, you have to keep in mind something quite important, which is the environment. C defines two environments. I'm going to use the latest specification, C11, although we're going to code in C99 because it's still the most widely used standard, and C11 doesn't bring that much that we want to know right now. Environment. You have the freestanding and the hosted environment. And the hosted environment is actually what your compiler and linker, the complete toolchain, builds to by default. We don't want that, despite some optimizations that it might bring. So Linux uses it, but they do tricky things for that. We want the freestanding environment. And as they should say here, in which the C program execution may take place without any benefit of an operating system. So basically, a freestanding environment is specifically meant for kernels. So that's one thing we have to do first. So one thing we need to do right away before doing anything else is telling the compiler to build for such an environment. And you do this with flags, with compiler options. You have to know your compiler. You have to read lots of options. Although one nice thing with GCC is that they're pretty well documented and relatively easy to find. So this is the option we want. Okay. Then, is that enough? Okay, it seems to be enough, although we link against the math library for some reason. I'm not sure why. I must have copied that. Yeah, I copied that from somewhere else. Oh, let's change the makefile so everything is out of date always. We actually want to track the sources, and the objects will be built from the sources. So you can't like no one can remember everything, and especially me, I have a very bad memory. So you have to learn documentation. You have to learn how to look for things and how to read them, how to read specification. Like be very suspicious of assumptions. Don't make too many assumptions and test your assumptions if possible. So here I want the documentation of GNU-make for pat subst. I remember it out of my head because I spent quite some time on the build system recently. So this is what I want. Variable pattern replacement. So basically I want to change the extension into another one. So pat subst, and Vim knows it, so it's going to use colors for that. The variable is sources. Wait, no, it's... Oh, okay, this is another way to write it. Okay. So the pattern would be C, and then O, then sources. Okay, and here in Phony, I'm going to include the sources. I'm telling Make here, I'm telling Make that all those files, all those targets are out of date, which means that Make is going to rebuild them all the time. How long has this been going on? We've just started. Hello, Sir Waffle. Is it possible to use freestanding environment for regular user space program? Yes, but you'll be very limited. Like very, very limited. So it's a good way to make very specific programs that are almost like kernels. And like instead of using the hardware, they're going to use raw system calls, for example. You can do that. I've been waiting for this all day, honestly. Really? But you're in the US, so how long have you been up? Okay, we have another problem, which is that currently, yeah, oh wait, we compile. That's weird. Yeah, okay, we have implicit rules. We have make implicit rules. I'm going to disable them. I'm not sure if you see here what's happening. We go straight from the source to the binary. So basically this rule here is completely skipped. And instead we have that one apparently. But here we have objects and they have not been replaced. So there is a mistake here. I probably need to use that. I forgot the name of that. Okay, that's better. Much better. But I'm still going to disable make implicit rules because they're actually not that helpful. And we do that with this. So let's actually comment that. Okay, or we could use this option. It's quite good too. And it removes the need to comment. Tell me if you think I should instead comment and no built-in variables. But I guess anyone reading this should be like, should understand what this means. Tell me if I'm wrong. What's been going on with Make thus far? Not much. We're actually not working on the Makefile itself. We're making it just good enough to work. It's going to rebuild everything all the time, but we have so little code that it doesn't matter. Are you going to upload the sources after each lesson? They're not really lessons. But yes, we have a repository on GitHub, which you can check. I should actually write it. Yeah, I'm going to link it directly here. Does that work? Oh, no, it doesn't. Okay, sources. Good, you can check that there. And yeah, I intend to make a couple of commits and Metal Snake too, ideally, every time we work together. So right now we're working on two things. I want the Makefile to work and I want the linker script to work. Literally left work early for that, really? Wow. So what's the difference? What's the difference between STD GNU 11 and C99? So when you read GNU, you have the GNU extensions, and GNU 11 is basically C11 plus GNU extensions, whereas C99 is strict C99 compliant without the GNU extensions. Good evening, how late am I? Not late, not late. We're just starting. Really. Okay, so I think the Makefile is in good shape.
Which rules exactly? Like, it's implicit now, but which rules would it, uh, or it's not implicit?
No, it's explicit. It's this one.
Now explicit. Yeah.
Yeah. Otherwise, again, yeah, you read the manual as usual. That should be a reflex, right? Or find a tutorial, search for it. But since I'm here to answer that kind of questions, let's take a look. Implicit rules. Yeah, you have a whole chapter about that, and it's actually quite complicated. Catalog of rules. Yeah. I think you can print them, but I don't remember how. But there are lots of files, extensions really handled here.
Gotcha. Okay. Yep. And they're saying I should increase the volume. Is it too low or?
The other voice is too quiet. Actually, I think I should do something. Don't change anything. I'm gonna see if I can change that. So be right back while I change those settings. Okay. Recording. How does that work?
Um, it's TeamSpeak.
Okay. Is that better or too loud?
That is, or I can hear you. Your volume increasing.
Okay.
On my end.
Yeah, but we need guys in the chat to tell us.
Yeah.
I don't understand how OBS works for that.
Um,
Desktop audio. Oh.
Desktop audio. Yeah.
Okay, so I would have to increase it and reduce. Well, how can I do that? It means
That slider takes it up, right? Or have you got it at a certain level that you?
the
In
problem. The
OBS.
problem is the music. Like if I increase your volume, I also increase the music too loud. Still crazy. Crazy how? So let's think for 1 second. It's not the playback, it's an output device. So recording, I put that at 50. It's actually 54, I think. Okay. Yeah, never mind. So there is a sync, right? There's a sync, and I don't know, so it's not applications, it's virtual streams, I think. Uh,
Maybe you could take it further on TeamSpeak. I mean, it's already.
Because if I increase in the chat program, it's gonna be too loud for me.
Oh, right.
So, sorry guys, we should have tested that better. How can I do that? How can I do that? I think the only way is to sacrifice the music right now. Oh, it's already at 50%. Oh. Okay, so I did something here. Or not. Okay, let's just cut the music. It's a recording. Applications. Okay, so how is that now?
Oh, that sounds extremely distorted on my end.
Sorry. Sorry. So I'm surprised because that's not what I thought I was changing. Capture default monitor, it's at 100%. So let's just change that in here. Volume. Yeah, you're already at 6 decibels.
It doesn't start clipping very quickly, though, does it?
What do you mean?
Well, I mean, when you boost the audio, it starts clipping at some point, but I don't think if you increase it further, it's the audio quality doesn't go bad necessarily.
Yeah, but that's not. It's probably not the right way anyway. Yeah, I agree, Laurie Master. I'm looking at Pulse Audio, and I have a monitor on the desktop output, which is used as an input for OBS. But I don't exactly know how to change the volume. It's really annoying, actually. Can you talk right now?
Sure.
Okay,
What do
so
you want?
let's see if that changes.
Right. Trying to
Okay, is that better, guys?
figure out a proper volume for my microphone.
So you could lower the volume for yourself, like your headphones, and upping it in the general OBS audio out. But I could do that, yeah. But I'm going to, I'll aim at the simplest solution. Is it better, guys? Like Metal Snake, if you talk
Is
right now, is it better?
Yeah, is my microphone better now, or is it still the same? If you could let me know, that would be awesome. Also, do you have a separate slider of volume uh, on your music player, or is that
It's complicated. The music player uses also. I think it's the same, maybe very slightly better. That's not it. Oh wait, we can do that now. Okay.
it
Uh,
should it should be better now, at least a little bit better?
so this means I can decrease it here, I suppose.
Is it still the same, or maybe reducing on the other one, or I'm not
Well,
sure.
OBS doesn't reduce as much, so it should be good.
Okay, okay.
Not bad. Okay. Let's adjust it slightly. 15 decibels.
Okay,
Minus
just
15
a
is
little
better.
bit.
Yeah,
That's
see?
better.
They're
Okay, that's
starting
good.
to hear it. Okay. So yeah, I can definitely not start the music right now. Anyway, um, okay. So back to this. We have the makefile. So very basic makefile, freestanding. There are still some switches that we need because I think, for example, that if we have, let's see, can we use standard files? I think we can. Yeah, we can. We should not be able to do that. We should completely separate what's in the kernel and what's outside. So again, compiler options. These ones are no std library. This one is really for the linker. I'm not going to have separate linker options though. Actually, I could. Let's have them. Okay, this is okay. These are spaces. So no std library, no standard library basically, and then we have no std inc. Which means do not search for standard system directories for header files. And this one would be so it's headers, so it would be for the C preprocessor. We can start doing that though. We can start having specific options for the C preprocessor. Here CPP means C preprocessor and not C++. What else do we need to move? Probably this. And GNU source, we don't need GNU source actually. I said C, well, it's actually going to be GNU 99. Let's say G3, or just G actually, freestanding. Okay. Okay, and then we may add more warnings. Again, this is not meant to be like very like exhaustive. It's meant to be simple, understandable, really the basics. And we're really interested in only those two things. Like, this is not really an argument. Okay. I'll comment that some other time. It's really not the point right now. So again, let's have std library. Let's try and rebuild. Did I save it? Yeah. So I forgot something. I forgot something in the makefile. I forgot to use the C preprocessor when compiling. The C preprocessor flags. Okay, and obviously I need the linker flags when linking. Okay, that's much better. We should not have stdio either. Okay. So right now we have a simple main, and as you can see, the compiler, well, actually the linker, is complaining about the start symbol. And the start symbol is the default, like it's the name of the default symbol, which is used as an entry point. So that's what we are going to write in assembly, but after I write the linker script. So, okay, good. We're going to use git ignore later for that, but again, this will be a separate subject, because that too needs to be, I think, explained some, like, quickly, but still. Some people don't know about it, so why not? Let's call it kernel LDS. Now again, I'm going to use something really simple. I'm not going to pre-process the linker script like I do elsewhere, which means that we might have duplication. That's okay. It would make the makefile a bit more complicated. We'll see if we do it or not, but we're going to start with something very simple. Also, we're going to start with a machine that has a fixed amount of memory, or rather at least that much memory, because otherwise you have to talk to the bootloader to know how much you have. It makes things more complicated. So we're going to assume a certain memory layout. Salut Zonde. Now, when using the GNU toolchain, if it's not the compiler you're looking for, like if it's the linker, the assembler, or other tools, what you want is actually the binutils. And you have all those tools here. And the documentation for them here, separated in a couple of different internal manuals. The one I'm interested in is the linker manual and the linker scripts here. So we'll have sections, but we already have default sections. We have the text section, we have the data section, we have the BSS section, and we're probably going to have a boot section where to put the, like, are we going to do that? We don't even need to do that, I think. We don't even need to place it at the beginning. But we need to place something at the beginning of the file because the bootloader, if you remember the multi-boot specification, which we're going to use right here, the bootloader checks for a magic number in the multi-boot header. So we need to provide a layout here. We need those three things here. So we'll have to place something at the beginning of the file. But that won't be a problem. That's the only thing we need to actually make specific in the linker script. Everything else, like almost everything else, is probably going to be standard. We probably want memory commands. I'm not using them in my in the X15 linker script because X15 doesn't know yet the boundaries of memory that way, but it will for ARM for some boards which have a fixed amount of memory. And here you can declare ranges, so where they start and how large they are. And we're going to declare one. So memory, let's take a look at the format. So name, we're going to call it RAM. Okay. Attributes, do we have different attributes? Like this notation is usually used for optional stuff. But if it's not provided, what are the values? I can't see anything default, so I guess we're going to specify them with the same name as the input section. If you define region attributes, you can use them to select the memory region. Okay. Oh, okay. So basically, these are inferred from whatever section we put in that memory range. Why not? This would be like, this is a very interesting example. For example, yeah, you have a ROM and a RAM. So read-only memory and random access memory. Read-only memory, obviously, easy read-only. So specific, the linker script specifically removes write permission on that range. And this one here is like everything else. Not sure what the exclamation mark does if an map section matches any of the listed attributes other than, it will be placed in the memory region. Reverses this test. Oh, it becomes the default for those that do not match the listed attributes. Yeah, okay. We're not going to use that. We're going to make it very simple. It's read, write, execute, allocatable. Actually, it's everything. Let's not even use any attributes. They're going to be inferred by default. So origin. Now we have to take care about a few. How could I call that? Historical issues of the x86 architecture. Can we find that quickly? Yeah, that's not bad. But Zlog, no, that's probably not it. It's probably too old as well. This one maybe. Yeah, this one will also be useful, I suppose. Okay, so this thing looks decent. At the beginning, you have a bit of RAM. This dates back to the 90s and even before that. And there is a famous quote, and I think it's actually an urban legend, but I'm gonna tell it anyway, about Bill Gates saying something like 640K will be enough for everyone. Let's actually look for this. It's a fun one. Won't go away. Yeah, but you probably didn't say that. Yeah, it's a myth. Okay. So yeah, basically you have to keep that memory map in mind, but not everything, not the details. What you must keep in mind is that you have two locations for random access memory. You have that, which we're not going to use because we really don't care about 640K. And then the real memory starts at 1 megabyte up until some limit. And for our system, we're going to use like 64 megabytes. Okay? Very simple. I closed it. No, I moved it here. And yeah, we could use that as a reference. Now origin. So 1 megabyte hexadecimals. This is probably 64K, so this is 1 megabyte, yeah. Again, when you use hexadecimals, remember that one digit is 4 bits. So that's 4, 8, 12, 16, 20, and this is bit 20 here, starting from 0. And 2 to the power 20 is 1 megabyte. What are the last 16 bytes for? The last 16 bytes. Oh, yes. This is the reset vector. So this is where the processor starts execution. Like the first, on ARM, for example, the first instruction is at 0. And on x86, the first instruction is at the last address. It's an architectural choice. So that's why I don't want to focus on the bootloader. Like I said, it changes too much from one machine to one architecture to another. This thing here is very likely mapped to some hardwired ROM in the firmware, which also contains the BIOS. So basically this thing jumps somewhere here, and it knows where. You don't, and you don't have access to that. It's read-only. Could you also repeat the digit counting for the hexadecimal you just did? Yeah, we could do it with, oh, these are F, but why not? Every digit in hexadecimal is 4 bits. Hexadecimal 16. So since you can store 16 values, you need 2 to the power 4. So you have 4 bits. So that's 4 bits, that's 8, that's 12, that's 16. And this one is up to 20. And actually from 0 to 19. Remember, it starts at 0. We usually count from bit 0. And so this is 4 bits set. But I'm not making, the point here is not to train about hexadecimals. I'm just giving you tips that are useful. So we are going to allocate something here. Now, one thing I'm not entirely sure how to do is to specify the length. How could we do that? I guess the simplest way is really to subtract 1 megabyte from 64. So we won't have 64, we'll have 63, but it should be fine. Hello, Little Fire Studio. Not to sound like a noob or anything. I think like this project is literally meant for noobs. So if you're not a noob, you're probably going to be bored, or like you'll probably know like a lot of it already. So let's compute that. Yeah, you don't know BC, Metal Snake, right?
I do not know.
Okay. So you have two variables that are used, that are very useful, which are I base and O base for the input base and the output base. And I'm going to use, for example, 16. Well, actually, does it make sense to have that in hexadecimals? I don't think it does.
I think in a example below on the manual page you have open, it says K after it. I think it says 2.
Oh. Here you mean?
Yep.
Oh, great. Let's be lazy. And actually they are...
So why would you choose to have 63 rather than 64?
Because this is the length. This is not the end address.
Okay.
Do you see what I mean?
Not exactly, no. So it starts at 1 megabyte.
It starts at 1 megabyte, and the length is 63. So the end address is going to be 64.
Okay, yeah, gotcha. So it doesn't like go over into the next 64.
It's just so that people can type QEMU -M64 and it works. Because otherwise they would have to type -65.
Yeah, okay.
And then they would say, why is it 65? You know?
Yeah.
So yeah, we'll have to explain that. I don't think we have... Oh, shit. I don't think we have comments in that. Do we? Script. Do we have comments?
Wait, if you go back one, I think it showed...
Ah, great, great, great. Okay, for now I'm only placing to-dos. We're doing the work, and basically the comment will be what we just said now. So it's for people who are not watching the stream, basically. I'm going to immediately add that file to Git so that I don't remove it by mistake. So we have run. That's a good start. Now, let's keep this image here, just in case, as well as the multi-boot specification. What do we need? We need sections. Let's see if we can find, if we can find a good example. This is the whole syntax, so it's quite formal. And you have to, ideally, if you want to really exploit the tools at their best, you'll have to understand that. What we're going to need here is basically, we're going to need a name. I don't see the name. That's probably the name. We're going to need output section commands, and we're going to need that region. And that's actually pretty interesting, but for me, for other projects. But this one is the one we're going to use because it says basically where to allocate a specific section.
In which piece of the memory?
Yeah. So let's take a look. Sections, okay. So the first section is going to be text, and we'll see about how to boot after that. You know, the header I mentioned. We'll add it after.
Sorry, what header?
Yeah.
Which header is that?
The multi-boot header. That one here,
sorry, yeah.
With the magic number, the flags, and the checksum.
Yeah.
Okay, now about the output section commands. Let's see. Section address. Okay, it's going to be something like this. But this should be described after. Yeah, basics. Okay, if you want to understand it all, you'll have to read it all. What we're most interested in is that form. So yeah, unsurprisingly, it comes first. It basically says, include everything that comes from the text sections in the objects that are linked. Same for the data. Actually, we could use this to match the way functions are written, but that's my coding style. You can do really, it really doesn't matter. Okay, we'll probably have, well, we may have other sections like read-only data, but we'll see. And then BSS. That one is a little special. We might have common symbols that we probably want to disable too. And I'll have to explain, yeah. If I can, I'll avoid common symbols because they're the kind of difficult detail that is not interesting for students. Okay, and now we want to move that into run. Like, we don't know where the linker is going to choose to allocate, well, to do the allocation. Okay, that should be it. Now let's tell the linker to use the the linker script. And this is done with GCC. So it's not, I don't think it's directly done with GCC. I think you actually pass that kind of options to the linker. And there is an option for that. which should be this one if I remember correctly. With a comma. Pass option as an option to the linker, if option contains commas, etc. So yeah. So let's take a look at the linker. Script. Oh, okay. Search directory -t. So it's going to be WL -t equals, or like, let me check how I did it in X15. It's going to be used as a reference often. Okay, this generates the linker script. And how is it? Oh, xlinker. Oh, there is an option actually. Oh, okay. I remember bad. Bad memory as usual. Pass an option as an option to linker. Okay. Yeah, it's probably better to do it that way. And I think, if I remember correctly, the reason I do that is because of clang, but I'm not sure. Okay, so -t, and then we have kernel LDS. Okay. So this seems to work. What we're going to do, and by the way, we're not going to call it hello, we're going to call it x1. Okay, now we're going to use readelf with the options A. So A means everything, all, and W is basically so that we're not constrained to a certain column size, a certain width. And we're going to check our addresses, and we can see here that they are indeed at around 1 megabyte. Which is quite nice. And we have the text sections. We don't have data or BSS yet. How do you know that linker script is working correctly and these sections are exactly as described? This way, exactly. You check it with that kind of tools. And I really like it's like when generating code with C. When details matter, check that what's generated is actually correct. So check the assembly, check the executable, the elf file, the sections, everything that matters. So now we have something quite nice for us. The elf format defines the entry point address, and here in the multi-put specification, the elf header is supported. Let's see where they state that explicitly. Okay. Compliant bootloaders must be able to load images that either are in ELF format or contain load address information embedded. So that other option is basically for older formats, because the multi-put specification is quite old. It has around 20 years, perhaps more. And ELF was just coming around in 97, like 95, I think, was the big merge. I don't remember exactly, but it was quite a mess for some time. And so we don't care about that. We use the ELF format. We let Grub use the informations or the information from the ELF format to load the executable where we have specified the addresses of our sections and symbols. When I run make, I get an error saying that int main saying it isn't a prototype. Oh, you mean you have cloned? Okay, well, you need to tell us your version of GCC, and int main saying it is in a prototype. Okay. I don't know, works for me, but wait for some more work, because like what's on the Git repository right now is not not very relevant yet. Oh, I closed it. Oh well, we don't need to remember that anymore. Actually, we can just close it. And normally the linker script is finished. Like, not finished, we'll have to add the headers, but it's mostly finished. Now what we need to do is a small script that is going to start QEMU with grub. And again, I'm going to copy that from X15 because it's actually, a bit tedious to write.
You did say the linker didn't include the BSS or data.
Yep. Because the reason is because we don't have any. Like if you check, that's a good question. If you check the main object, which is the only object we have right now, the size is empty.
Yeah, okay.
So the linker knows that it doesn't have to allocate anything. All right, let's make it simple. No number of CPUs. KVM. Okay, amount of RAM. I'm going to hard code this actually. Does that make sense? Probably not. Yeah, that does. Okay. KVM, no, just enable KVM. If you don't have it, well, I suppose it's just not used. I don't remember exactly. Control grab is just some stupid option, so that you use the control key to capture the mouse. GDB creates a TCP port for GDB access. This is going to be useful and explained. So memory is 64. We have only one processor, and the rest is good. Okay, let's see if this works. Normally it should not. Oh, enable KVM not found. Oh wait, yes. Okay, that's better. Now I don't expect it to boot precisely because of this. No multi-boot header found. So that's what we're going to fix. And that's going to be the last thing I do before you take the wheel in a couple of minutes. No pressure, of course. Okay. So we need to tell the linker script to put something at the beginning, because in order to be compliant with the multi-boot specification again, we need a header. We need this. We need 3 integers of 32 bits with the magic number, which is specified somewhere. Must be this. Then we need a couple of flags. I think we'll have no flags, really. What do we want? All boot modules, we won't have any. Memory, we are using fixed memory sizes. Video mode, we won't be using the video. Not yet. And if we do, we're going to assume some legacy configuration. Yeah, okay, so that's legacy. We don't want that neither. The field checksum is a 32 bits unsigned value, which when added to the other magic fields must have a 32 bits unsigned sum of 0. Okay. So basically when when it's added to this and this, the size must be 0. So it's basically 0 minus the others. Now, can we ask the linker to do, like, to allocate something before anything else? Can we do that? Section constraints. So I've never really done that with the binutils, so we'll see. No. You can assign a section to a previously defined region of memory. Yeah, there is a simple example, but it doesn't say how. Well, how to make things, like how to order inside. Output section field. No. Section attributes. No. One thing we could do is just rely on order, but I don't know. I don't know if it's if it's guaranteed by the linker script. Do you see what I mean?
The order in which it's stored in memory. Or...
Yeah. So basically here we have one region and 3 sections. And what I want to do, oh, wait. Yeah, what I want to do is force something at the beginning of RAM, right?
Mhm.
And I don't know if I can do that without creating another region. I'd like to avoid creating another region. I'd like some constraint that says this comes first, you know? So I'll try to find that, but if I can't, we'll not waste too much time. Okay, so we have some ordering. Ah, it's for overlay. Maybe not what we want. Let's use Google. Commands. Let's check the other commands. Entry point, that's not it. File commands include input group as needed. No. No. Oops. Oh wait, maybe I didn't read. Controls the actually where input sections are placed into the output sections, their order in the output file, and to which output sections they are allocated. Okay. So I suppose, but again this is an assumption, that they are allocated in the order they are declared. So if you not use a section, then you can place each into an identically named output section in the order that the sections are first encoded in input files. Okay. Well, let's try that and see how it goes. So we'll call the section header, and it will contain header. Now, when we link, we don't have a header section. So again, like data and BSS, it won't really matter. So let's have one. We're going to write an assembly file, which we are going to call boot s. The reason for the uppercase S is because GCC, the same way GCC interprets C files ending with C extensions as C files, is going to interpret files ending with an S as assembly files. And then you have a small difference between lower S and upper S. Upper S is also pre-processed, whereas lower S isn't. And having macros in assembly is also a nice thing, so why not? As usual, yeah.
Should you be putting the header also into RAM? It has the angle brackets, or it's missing the angle bracket RAM at the end. Not
Oh
sure what this
yes,
is.
you're right. You're right. Yeah. Don't worry, we would have caught that when checking the binary. So again, binutils. This time we're going to look for the assembler. Documentation. Assembler. GNU assembler, gas. Weird name, but whatever. And now we're going to look for, yeah, sections, especially the directives that are related to sections. So there should be a section here. Section name. Okay. And you can actually have flags too. So we want to create a section HDR. And in that section, we're going to have the, the header. So long with the value. When I write long, again, if you want, we can look at what it does. Long expression, the same as int. I could use int actually. Long is probably a bad habit here. Expect 0 or more expressions. Emit a number that at runtime is the value of that expression. So basically, you are literally writing this value at that location. So this is the first value that will come in the section header here. Oh wait, people are talking. My version of GCC is 6.3. Okay, same here. Hello, Queen of Noob. Is that a RAM or a RAM? I can't read it very well. Oh, it's greater than. So how do you call that symbol actually?
I looked it up the other day. I think they're called angle brackets.
Angle brackets.
Yeah.
It makes sense, right? Curly brackets and angle brackets. Okay, and square brackets. Okay, so yeah, it's an angle bracket. And again, you can find that on the binutils documentation. Hello, Michael C. So, for example, if I just do this, okay, and I build, and I take a look. So this disassemble, okay, this is like readelf. This is part of the binutils suite of utilities. -D tells the tool to do disassembly. Okay. Oh wait, I need the other version. I'm going to show you why. Disassemble, and here disassemble all. This one only disassemble sections which are expected to contain instructions. This one disassembles all of them. And this is not something we made an instruction here. And apparently it doesn't work that well. Wait, why am I disassembling? Yeah, the kernel. So it doesn't seem to work well. We'll have to debug that. Yeah. Okay. So we have main and we have the infinite loop, but we should have had something before. Oh, obviously I'm not building the assembly file. Stupid mistakes always. Oh, by the way, we also want to include the assembly files here. So S into objects. That probably won't work. No, that probably won't work. Wait. It's probably on the result. Okay. No, still doesn't work. So when you want to debug makefiles, you can use the info command. So this is, but did I change the sources? Like, how retarded am I? Yeah, that's better. And the makefile has no rules to build assembly files. So let's make one. Actually, I think it's going to be the same rule. No rule to build. Wait, yeah, I need to change that. Okay, that's better. And now, when this is assembled, we do have the header with the appropriate values. Okay, so that's good, but that's not complete. We need
The flags and the checksum, but in this case, the flags are missing, or 0, I guess. Right?
They can't be missing. Oh, wait, what am I? Sorry. So 0, we have no flags, and then the magic, so what am I doing? The magic is going to be basically minus this. So what we could do, wait, I'm going to do something simple. Again, I'm going to take what I've done in X15. But it's probably something quite, yeah, it's a minus, basically, exactly. So it's basically minus this, because we don't have options. But you know what, let's do it right. Let's have macros. And let's define them here.
When you look at it later.
So boot header magic. Okay. Then the flags. And yeah, we don't need that. It's computed dynamically. And then, yeah, we have, so the flags, wait. The flags plus the magic number. Is that right? Yeah. And minus all that. So minus because the sum must be 0, basically. So it's like starting from 4 gigabytes. If you look at it this way, this is 4 gigabytes. And your registers can only store values from 0 to 4 gigabytes minus 1, right? Is that something, is that difficult for you to understand MetalStake, or is it almost obvious?
Well, it ends at that address, doesn't it? I mean, it starts
ends,
at
but
1 minus 1.
What I'm saying is that this value cannot be stored in 32 bits. It's 33 bits.
Yeah.
Okay. So this means that this bit here actually goes away, and you end up with 0. So basically what's happening here is that we're doing this. That's what's happening.
But it should add up to...
Yeah. Like,
oh, okay.
You see?
Yep.
When you add them, you have 4 gigabytes, that bit goes away. That's the trick. So it's 2's complement. All right. So now we have a multi-boot header, we have an entry point, so we should end up in an infinite loop. And with an environment that No multiple header found. Oh, there is another constraint. I forgot. The multiple header must be contained completely within the first 8 kilobytes of the image and must be long-word aligned. And in general, it should come as early as possible. Now, why is that not the case? Again, we use readelf, which is a very important tool that you really need when doing that kind of things. And we see that the offset in the file is very large. That's a problem. Actually, I'm not sure why the file is so large. I think I know. Or do I know? Oh, it's 64 bits, that's why. We're going to make that 32 bits. With an option which is M32. So again, man GCC, M32. It's not specific to x86. It's actually very common. No, it's not that one. Generates code for 32 or 64-bit ABI. And this thing is probably not an x86. It's NVIDIA PTX. So apparently GCC can generate code for GPUs now. Why not? That's weird. Okay, so the linker script here is not aware. Okay, that's why. We need to change the makefile again to add M32 to LD flags as well, I think. Yeah, okay. Let's take a look at what readelf says, and now we have sizes which are much which make more sense. So the reason why on 64 bits it's slightly different is because alignments are 2 megabytes because of large pages. So I'm not going to explain that into details. If you want it to work on 64 bits as well, the trick here is to do something like this. Tell the linker that the pages are 4K. Don't ask me how I found that out. I guess it took me a lot of time and a lot of research on Google. Okay, so we have something that that links, that boots. Wait, we have, oh yes, we have that here. Okay, make clean, that should work. Okay, so we have a very basic environment from which we can start coding. And you can see here we are in an infinite loop. EIP, the instruction pointer, is precisely this. So let's take a look. Oh, you can see something though. You can see that the order is not enforced. Do you see that? Where's the text? That's weird, isn't it? They have the same address. And I wonder why we have those program headers. But it's like, oh, it's linked dynamically. No, that's not good. I have to change that as well. Yeah, I forgot that. It has to be linked statically, of course. No memory region specified. Ah, that's right. Details. Even when you want to make things simple, there are so many details. Okay, so it's the notes section. We're going to discard it. Is that notes? Note maybe? Note GNU build ID. Okay. Okay, now I get a warning. Let's find an option that disables the build ID. So the build ID is a feature that is used to make sure that the binary is always the same, that the binary really doesn't change.
How do you mean the binary doesn't change?
That when you extract a binary, for example, from a firmware, you compare the build ID, and normally the rest of the binary should be strictly the same. So it's not that it doesn't, like, it's not preventing changes, but it's a way to encode an identity of a build inside the binary itself.
Ah, okay.
Okay, so makefile again. Okay, so now I don't even have to discard it normally. Great. Okay. Now I'm a little surprised by this. We have load here. We have a first section, then we have a stack, but this one is probably not used. And we have a text and EH frame, which is for debugging. It's debugging symbols, basically. And I don't see the header section in this. And I'm slightly worried because it's here, but at the same time it's here. See? It occupies the same location in memory, and that's not good. So one thing we could do instead is not have such a section, and I really don't understand why the allocation. There is some overlay apparently. Let's take a look at that. No overlay. Okay, so I'm not really sure why this kind of allocation fails this way. It's almost like... No, I don't know. I really don't know. Salut Jock, ça fait un moment. Why can't you compare SHA-1 or something? Because the binary may be stripped. It may be changed in other ways. Or it may be converted into, for example, a binary format or an S record format. So yeah, it may change. The file may change. But the code in it should not change. Okay, so I have to find out why these two sections overlap. And I have no idea. What I'm fearing is that we'll have the same problem with the other sections. And I don't know, I really don't understand.
Does it have, or might it have to do with alignment, or?
No, probably not. Section overlap in LD, but it's AVR free, so I really don't know what compiler it is. GCC, okay. What is surprising is that the build doesn't fail, the build works. section start. Okay. Do I need... No, I shouldn't need a dot. Yeah, I wanted to try using memory, but like if it's taking too much time, we'll fall back to the way it's done in X15. But I'd like something. What is that too? Oh, all right. Maybe I should do that. Okay. Yeah. Hello, Slayer-Darth. What are you making? Well, as the title says, we are writing a very small kernel for educational purposes. So something simple, but which gives pointers to all the tricky stuff that people don't know about and that is considered a bit frightening and that usually prevents people from even thinking that they may be able to do it easily. Actually, it's really not that hard. But sometimes, yeah, you have this kind of issues. Okay, so yeah, this is what I want. The program headers. AVR freaks and of course close and post everywhere. I don't know AVR that much, to be honest. It's the third. I think it's the third most popular architecture, and I don't know much about it. Oh, sounds pretty cool, isn't it? Okay, so it's going to be very simple. We're going to have a header. So here, ptload, yeah, we could actually check the documentation at the same time. Program headers. ptload indicates that this program header describes a segment to be loaded from the file. So everything else is usually interpreted by the dynamic linker. So LD, but not the LD you know. This one. Wait. Yeah, this thing here, which is actually a program. This is the linker, like the dynamic linker, which is actually the first program run when you start a dynamic executable, a dynamically linked executable. So Bash, for example, you can see the interpreter here. It's basically this one. And this is what starts. And this thing then loads the code, and the code then loads its libraries. And some time after, it's going to run main. But there is actually a lot of things happening before reaching main. So this is really the only one I'm interested in. This one is it's unused, so I suppose it's basically used to discard sections. Then we have flags, and those flags are classic Unix permissions. So we're going to use 4 for the header. Then we're going to have text. Wait. 5, yes, 5. Executable and readable, but not writable. Then data. And this one should be 6. Writable, readable, not executable. Okay, and you can see here this format. Does that will work well with RAM? It should, right? So name type at flags. Now sections. Yeah, okay, this is where it goes. Let's actually look at how sections are defined. Description here. So we can have region, and after we can have program header. And many of them? That's weird. Okay. But we still have this problem. We still have overlap. Whereas here we don't, for some reason. That's actually really weird. Oh, by the way, wait. I'm forgetting something important. We don't have a start symbol. Hello, load.
Oh, yeah,
Doing
that's
good, doing good.
the one it asked for at the start when you didn't.
Yes, how can it work without a start? That's so weird. I expected errors. Yeah, it can't really work. Well, it works because we have the text here, but we want the header here. And somehow we have both. Like, for example, if we run this, QEMU is not complaining. The instruction pointer is correct. And if we take a look with GDB, we're at main. So how does that happen? Oh, yes. Oh, yes, obviously. We don't really care about the header being in memory. We care about the header being in the file here. But it's not loaded. That's why it's not loaded. Although this here should have made it loaded. So yeah, we don't want the header to be loaded. It makes no sense because that's not what the entry point is. So okay, why not? This also means that we don't need it to be. We need it to be located in the file. So you have two images here. You have the file image and you have the executable image. Or execution view, if you prefer the word view. Elf is the file. This is how the bootloader is going to view your code first. And so yeah, we can have the same address because this is in memory after loading. And but here you can see, for example, that the offset inside the file is not the same. And this is actually the one thing that the bootloader is looking at. Now, what I don't understand is that we are loading this, but for some reason, it's empty here. Like, we don't have data. That's okay, we don't have data yet, but we should have the headers. So I'm going to take a look again at the model, which works. See what we did wrong. Okay, so maybe we need flags. Oh, the code 32 would be nice, actually. Flags. It's basically... Let's take a look. In utils, documentation again. New assembler. Section. Okay, so what are the flags? PSS section, section not loaded. Oh, that's nice. Section not loaded. We could use that. How bootloader searches for the header by section name? No. It says here that the header must be contained completely within the first 8 kilobytes of the OS image, so the file image. So basically, it's going to look for the magic symbol, this thing, in the first 8 kilobytes. And that's why you have a checksum, because you might find a magic value by mistake because there is like code that is encoded to this value, but it's very unlikely that the checksum would be correct then. So it's really testing each word, and that's why they say that that it should come as early as possible. Okay, so what we could do is actually tell it not to be loaded, but then we have to specify where it comes in the generated file. We want it at the beginning. Now the kernel is going to be so small that everything is probably going to be less than 8K for a long time, but maybe someday it might be bigger than 8K and it will fail because the header is going to be at the end, which would be an annoying bug. Yeah, hacks, yeah. So N, section is not loaded. That's actually a nice flag. What else do we have? Variable section, data section, exclude section from linking. No. Oh, A is ignored. For compatibility with the L version. Oh, this is the COF version. Stupid me. Ah, okay. Section is allocatable. Okay, that's probably why it doesn't work. Now we could have the header section loaded too. Like it doesn't hurt to have it loaded. I'll see if I can make it better, like not loaded into memory, but still at the beginning of the file. Okay, target specific. Oh, and then we have the type. Okay, so it's allocatable, and that's it. Does that help?
What is the code 32?
It means that the generated code will be 32 bits.
As in the words will be 32 bits, or
No,
isn't that?
no. You can't really look. This is x86, so instructions have variable size, and this is very small code. Let's take a look at. I don't have a 32-bit executable, but it's basically the same in 64 bits. The size of the instructions vary a lot. See, you have very big ones and very small ones.
What forces it to 32?
What it means is that it's meant to generate code for a processor running in 32 bits mode. So expecting the ISA of 32 bits instructions. Basically this, if that makes more sense.
Yeah.
Alright, let's take a look at our image. It's already 10 p.m. Time flies. Now we have it here, but you can see that it's after the text startup. So now it's, yeah, I think the A flag is important. It's allocatable. So it has to be, so this makes sense because of allocation. Whoops. Let's take a look at the assembly. So this time we have main here, and you can see here that we have the header, which comes after. And yeah, the reason it comes after is because I removed it from here. Okay, now it's really at the beginning, and the text is even, okay, it's linked after. Okay, so I'm gonna do the same thing I did on X15, which is discard the debugging, the embedded debugging symbols.
just to make the disassembly cleaner, or
No, so that it doesn't take up space here.
because that's not something we need?
No, it's not. And it's absolutely not something we need with Grub, because Grub actually looks for debugging symbols, like the complete table of symbols from your ELF file, extracts it, and passes it to you. So you can fetch it back. And
Okay.
but yeah, this is something I'm not able to explain yet, like completely. That's why there is this XXX here. Okay, these debugging information are not loaded. They're elsewhere. So this means that we can strip the file completely. We have nothing else. Oh, we have a command section still. I don't know why it's still here, but basically we should only have what we have actually written and made available in the linker script. And that's basically our code. We have a header, and we have an infinite loop. And now I'd like to see EIP have this address. Oh, entry point isn't in a segment. Okay, we need an entry point. Yeah, we need an entry point. That's right. So let's have it. We're going to write it in C. I don't see any reason why not. We can actually do that. No previous prototype, that's right.
That was the error Sir Waffle was having earlier. Sounds like it.
Ah, maybe. But that means he changed a few things, I suppose. Okay.
Well, that was for main. I'm not sure.
Okay, the address is correct. So we now have code that boots. So yeah, when you know where to look, and of course I've already worked on it a lot, so I have I have code I can copy from, and it makes the job much easier. But that's also the point of this little project, right? To make some of the simple things, the simple tricky things available. So now we can commit that, and then it's going to be you. I'm not going to be very picky about the Git logs like I am on X15. So just freestyle, simple.
The main thing is the code, and the perhaps the videos, depending on what you end up doing with them.
Okay, I'm giving you 2 shells. Normally you have access to the graphics, okay. And you have your copy here that you must update. Oh, there's a patch already. Did you make this patch? Or was it me?
I didn't do anything, no.
Okay. Okay, so you can basically pull everything and start, and it's going to be mostly you.
Mostly me, okay. Let's see.
Git status again, check if you pushed everything. Let me take a look. You can work on the machine, I'll be on my laptop. Although I need the IP address. There will be a copy of this stream somewhere. I'd love to watch paying attention later. No, I just cannot. I'm probably going to highlight the videos, and if Twitch cannot keep them, I'll probably upload them on YouTube. Yeah. Okay, 112.
So what exactly is the patch?
The
You said there was a patch, but
Oh no, I removed it.
okay.
I don't understand why it's there. So that's probably a leftover from work we did. Just one thing though, because you're going to enter your passphrase every time. So let's fix that. Okay. Let's try not to close the terminals. So yes, C8. Apparently I did push everything.
Did you here as well then, or
Oh yes. Unless you want to use Git, well, Git push really on a single terminal. It's your choice.
there we go. Right.
I don't have a YouTube channel right now. It's just simpler if we only use if I only use Twitch, at least for me. No. You have to pull the changes. So that's, oh yes, that's your repository. Okay, so let me just take the commands for a second here. Okay, and all right, so this is your repository, right?
Oh, okay.
So you have to
So
update it.
just
So,
fork it again.
yeah,
Or
I'm
something.
gonna show you how you do that with Git. So let's add mine. Let's call it Arbrone, which is, oh, it's yes. Let's actually go there. It's this thing here. Okay, now I'm going to fetch it with all the branches. Well, actually all the remotes. And now you're going to see that remote branch. And what you can do is merge, for example, the remote branch into your own. Git is going to see that you haven't diverged from it, so it's going to apply it fast forward, like this. And in your history, it's basically going to just be linear, no merge, nothing. And now you have everything, and your branch is still tracking your repository. So you have merged my changes into your local branch, and you could push them into your own repository like this. Now your own repository is up to date.
And then eventually, when we want to make the changes to the main branch, then I just have a pull request.
Yes.
Again. Yeah. Okay, that makes sense.
I believe that Twitch only keeps streams for 30 days. Not if you highlight them, but there's probably a limit on how much you can highlight. Okay, so yeah, try building it, playing with it. Now we're going to decide what to do next.
It's just make, right? Oh.
Yeah, it should be just make. Okay.
Okay.
And does the QEMU script work for you?
Was it? There we go. And then, what is the?
That should be it, only.
Okay.
Oh, you don't have. That's right. You don't have access to KVM. We'll have to relog you. It doesn't work. That's weird. Okay. So now we have to relog you, so that you have the right groups here, which you don't here. It's not automatic. Which means restarting the agents. Yeah. And you can add your keys. By the way, who is the person you're speaking to? It's Metal Snake, as mentioned in the title. So he's a student, he's learning. For now, I've been doing most of the work, but I'd like to see what he can do. And for that, we'll have to decide what to do. So yeah, retry the QEMU script, see how it goes. Oh, you use tabulation for
I
auto
did.
completion.
Yeah, it doesn't have
You're
boot
not in the
loader.
right directory.
Oh wait. Uh, okay. Nice.
So you'll have to learn the QEMU modular commands, but basically what you really need is just info registers. And then you also use GDB for that. So it's
So the command is info registers.
yes, but in QEMU, you're not running QEMU
Wait.
right now. Yeah, just info, and you have autocompletion too. Info registers, I mean, just info registers.
Okay.
Okay, so you should have read about those registers. At least the first 3 lines should be somewhat familiar.
Yes.
Okay, now the rest is just segments. We're not going to use them. And actually, wait. No, actually, we have to use them. Oh, so we can't really have the start symbol in C. We need assembly, but we can have it in C, and then go back to assembly, and then go back to C. It's a little complicated. Let's start directly in assembly. And the first thing you're going to do is actually make us a little more compliant with the multi-boot specification. So basically the OS image format is done, but then what we need is the machine state. And here is how it goes. The bootloader invokes the 32-bit operating system. The machine must have the following state. So this is what we expect from the bootloader. We expect this value in EAX. Do we have it? Yes, we have it. So you have to check that. And then we are not going to use the multiple information structure, but basically just checking that is enough. Now CS, DS, all the segments must have must describe a flat segment from 0 to the largest address. All those details you can safely ignore, except probably this. This is the interrupt flag, so basically it means that interrupts must be disabled for obvious reasons. Everything else is undefined. So yes, we'll need a stack, and that's probably we can't start in C directly. We need to write some assembly code, obviously. So this is also important. Even though the segment registers are set up as described above, the global descriptor table register may be invalid. So the OS image must not load any segment registers until it sets up its own GDT. Now we could load a GDT, but we can also use what the bootloader made for us. I think it's simpler. Like, let's not dive into that kind of details. The stack is going to be important. Checking the magic number is going to be important. So let's do this. So first,
When you say checking the magic number, what exactly do you mean by checking it?
I mean not booting if it's not that value.
Okay.
So we don't have any output for now. Okay. So the only thing you can do right now is like an infinite loop. And maybe, we can write like a character on the screen, something like that, as a very low level in kind of output. First, move the entry point to the assembly file. The entry point is in C. Yes, sorry. So you can see here, these are the virtual desktops. We're here. This is the one you have been assigned. So everything here is yours.
Okay. So we're moving this into assembly.
Yeah, and you can keep actually the main function in that file because we'll have to call it later. And main doesn't require a prototype, so you can remove the first line.
This kind of okay. Is this what we're going to be putting in boot as well?
I don't understand what you mean. Oh, yes.
Start.
Yes, the assembly is obviously for now. Boot is the assembly file. So, do you see where to write it? And do you see what you need to do?
No, I don't know where to put start,
Okay.
honestly.
So, you have to keep like the global view in mind, which I know is not easy at first. This is text. This is your code. So every code that you write, unless you make special sections, but by default the code must be in that section. Currently you are in that section. You've told the assembler everything that follows must be in that section. So the first thing you need to do is change the section, and then you'll need to write the code. And I'll show you. Yeah, I'll show you on the fly how to do what you need in order to achieve this. Tell him you can use and at the end of command for running them in the background. Here's one command line waste unjaded. Yes, that's true.
Yeah, that's what I was thinking. Is there any flags that we need?
Yes.
Because this is also going to be...
Yes, but you can show the documentation. It's on the right. On the yes, on that virtual desktop. And I think I have the AS section still open. Yeah. And normally you have the flags right here. So be careful. Like if you go up again.
Yeah, this is a different...
Yeah, ELF. This is for ELF. So that's what you need. Now what you really want is the flags.
Going to be executable?
Yeah. Has to be allocatable and executable.
Okay.
Probably not writable. No, not writable.
Because it's not a data.
Yes.
Section.
But sometimes you also want to mix permissions, like have executable code writable. Of course, if you have self-modifying code, that's one reason. But also if you want to compress your code so that you don't have gaps between the code and the data. Basically, if you want to merge them into a single section.
Okay. Is this also something we need in this section?
No, because it works like section. It says that everything that follows is 32 bits code.
Oh, this is just something you need at the start. Okay.
Or if you switch in between.
If I were to switch to header after this, I'd have to...
No, I mean if you switch to 16-bit code or 64-bit code.
Sorry. Yeah, okay, that makes sense. So what we're doing here is adding the start
Yes.
to text.
Yes.
So it was a function. I'm not sure how you would do that in...
Okay, so I'm going to show you quickly. Basically, you declare your symbol and you use a column. And then what I do personally is that I indent with 1, but you can use whatever indentation level you're comfortable with. And so we have the start symbol here. The next thing we want to do is check the value passed by the bootloader. So I'm going to let you with, you remember the big manual, I suppose? This one? Yummy.
Yeah.
And so you're going to have to find here how to do that. I'm just going to give you a few pointers. So AT&T syntax, that's what we use if you're looking on Google. You want probably CMP. You want jump. You want MOV. Obviously, you can't do anything without MOV on x86 and on practically any architecture really. And that's basically it. Although you might want a conditional jump, but you'll see that later. And yeah, I can do that. And you're starting here. Okay, so now it's up to you.
So the first thing we're doing is comparing the magic number, this one.
Yes.
So look, the load. Wait, is there somewhere we can look for this? Was it disassembly?
Oh, Q to exit the pager, and the disassembly is option. Oh, you don't have it. Okay, like this. But this here is not really usable as assembly source.
Yeah. Okay. Because I don't really know the commands all that well. Let's see. Look.
So I give you the pointers in the comment. What you're looking for here is CMP.
Oh, you don't have to load. Oh, because it's already in the register.
Yes, it's already in the register. That's the machine state. It's what the bootloader promises you. It's a specification is kind of a contract, and here the contract is that when you are started, when your code is started, there is a certain machine state where the AAX register must have this value. We're only checking that we have correctly been loaded by a multi-boot compliant bootloader, nothing else.
So this would seem like the one to use. And is it? I've seen syntax like this. Is that what you use, or is it?
It's close to that, but yeah, you're right. You're right, Laurie. But I don't know how to do that because I don't want to be the only one doing things, And I'm afraid that how could I do that? I'd like to give you a template, but you should use Google, for example, and like x86 CMP, compare two operands, and you're gonna see things like this. Now, I emphasize the AT&T syntax. Oh, you have a book for right? Okay, a book for this. So here you can have examples of how to do it, but I think they're not using the AT&T syntax. Yeah, it's like this. Okay, so I'm gonna just tell you those things as we go. Basically, yeah, it's CMP. Okay. So let's see what Sir was suggesting. EAX value or something like that. It's close, yeah. So CMP is the instruction. If you don't give a suffix, the size of the operation will be determined from the operands. Here, when we use a percent symbol, I think the name is a sigil, exactly. It means register. So EAX is the register we're supposed to check. Then we separate the operands with a comma, and then we use the dollar for immediate values. And then you would use the immediate value to compare here, which would be the magic number, but on the side of the operating system.
Which is this.
Careful, hexadecimal. Okay. Yep. So now you can check what the CMP instruction does. So the way a processor does, it's almost like it's the same on almost every modern architecture. Instructions that test stuff or that have side effects on the state of like that report things about the operation, basically, are going to modify what is called a flags register or a status register. In this case, it's the eFlags register here. So it's not interesting to know all the bits. That's not the point. What is important to know is that here, for example, a comparison is actually a subtraction between the two, and the result is going to be less than 0, 0, or greater than 0.
Mm-hmm.
And yeah, Faki is giving it all, except it's not put HDR magic because it's another value, but it's close. Yeah, half-endless loop or dot. Dot is actually the current instruction address. So do you see G and Z, G and Z in the chat? J and Z. What Faki said.
Oh yeah, that's jump when not 0, or
Exactly.
jump. Yeah.
Jump
Yeah.
if not 0. So this is a conditional jump, and you can actually check here how it works. So you compare, for example, and in the description of the operation, you're gonna have. So we're using one of them. Here it's Intel syntax, so it's reversed. So we're probably using. Oh, we should probably reverse those two. It's probably going to be encoded in a better way, but the assembler may be smart enough to do that for us. I think we're using. I don't see it. The order is normally reversed, so it should be this one but reversed. But I don't see any form where the immediate value is actually the first operand. So I suppose the assembler is smart enough not to enforce the order here. Instruction operand encoding, description. Okay, in the description it says that it's going to update the status flags in the eFlags register according to the results. This is described in the basic architecture, I think. Condition codes. I think it's that. And you're going to have the bits here specifically, and the one we are interested in is this one. Below or equal, not above. Wait, no, this is another one. Wait, instruction subcode, condition tested for CF or ZF is 1, this one is 0. Okay. Where is the equal one? Not equal, not 0, should be this one. And of course this one too. I don't understand exactly that, but I mean, I don't go into the details of the assembler here. Jump if non-zero works, and that's really what I want people to remember. The mnemonics have a meaning that is usually like very close to what it actually does, and normally you really don't need to care about the details. Just know that some instructions update the status flags, the status register, and other instructions may act differently depending on the state of this register. Okay, that's really what you should remember here. So then we have JCC, jump if condition is met, and you have a whole bunch of them. And we're using jump if non-zero.
Okay. Is this something you would do? Using this direct value, or
What?
or would you get it from define?
Yeah, you can create a macro for that too. But it's not that one. The value is different, be careful.
You add another define.
People are trolling about GitHub. Yeah, you must change the value here.
You could either do this.
No.
No, just
What?
have the.
Oh, yes, you want to have an or, right?
Yeah, exactly. Yeah.
I don't see the point personally, especially since the specification mentions two different values, not one built from the other. So let's just do the
Right.
same. Yes. You can write a dot here. Okay. And now we want a stack. So that's another interesting thing. Um, we want a stack. You can choose the size you want, but it has to be large enough for your kernel to run. Um, and we can make a decision like an arbitrary decision, such as we want our stacks to be 4K or 8K. So we can have a macro somewhere. Like we could have a file named defs.h for our definitions, where we're going to put everything, or parameter like param.h. You decide. I don't really care what we do here.
And
I
you
just yes,
include them as well in.
and you include it, yes, and it's going to be oh, not here, not here. Wait a second. We're going to just first we're going to create the stack and then we're going to use it. We could do that in assembly, but I'd like to have as little assembly as possible. So we're going to do that in C, in the main file, basically.
Oh, this is inverted somehow.
It
Can't use the.
doesn't work. Yes, it
No.
might be. It might be. Wait, here you go. Okay. So how would you create a stack?
You create an array, I guess.
Okay.
And you. For this, would you have a global? Or
Well,
is this?
would it work if it weren't global? Do you see any way it could work if it wasn't global?
Well, I mean, if you have anything outside of your main, then you can't use that stack. Unless you.
You can't, like, what you're saying makes sense, but it cannot make sense globally because main cannot run without a stack. If you see what I mean, you have to
okay.
you have to set the stack up
Yeah.
because you want to call main.
Exactly. Yeah. Okay. I think it's a good. Oh,
What do you want to do here?
the int types, I guess.
So we don't have, again, we don't have. We are in a freestanding environment. We have very few headers, but yes, one of them we have is this one, which is probably what you wanted.
Yeah, and these for the stack, it would be 32-bit.
So it can really be anything. It's a int, you int. If you use 32, it means every cell in your array is going to be a word, basically. It also means that your array is going to be aligned on a word boundary, which is good, so why not? But then it also means that the size of your stack cannot be expressed in bytes. It has to be expressed in words. So you choose.
Oh, that's true.
Hello, Zilpai. Oh yes, by the way. Here you go. I'm talking to Zilpai in the chat, don't worry.
And we'll be making these.
So wait, the type is wrong. It's an int.
Oh.
And aligning the stack is actually something we might want to have. So we have two ways to align the stack. We can declare it using a type which implies natural alignment. So if we use a 32 bits integer, the compiler has to align it on 32 bits. And we want the stack to be aligned on 32 bits because it's easier for the, well, I think it's also required by the ABI actually. So we really want that. But there is another way, which is to use a compiler attribute. And actually, if we're using C11, there is even a standard way without a compiler attribute to do that. So we have choices.
Would you say it's easier to have it per byte in the stack, or?
I would say that it's easier for people to count in bytes, and that we should use a compiler attribute here.
Okay. And the size of this would be. Wait, this is way too large. How big of a stack would?
4K is fine. 4K is fine. Yeah.
Okay. And the attributing is.
Oh well. Okay, I'll make that myself because let's be. 1 second.
Oh, sorry.
So GCC manual. You take the version you have, so we have 6.3. Extensions to the C language, it's an extension. Compiler attributes usually are extensions. And here we have declaring attributes of functions, and then we'll have attributes of variables, common variable attributes, aligned. So that's basically how you do it. Whoa, what just happened? Okay, and we want to align on 4. Here on the we shouldn't use that. We should use a macro that comes from the definition files because we're going to need the size of the stack when we set it up in assembly. When you create new files, immediately add them to Git. Because if you make a mistake, you might lose your work. That's a very important habit to get.
Okay. All right.
Now,
So we.
yes.
We have the stack.
Mm-hmm. Now we have to set it up. Do you understand what I mean when I say we have to set it up?
No.
Okay. So it's very simple again. Processors are really dumb. They have a couple of registers, lots of instructions, and not much else. I mean, that's the basic common ground. Processors are getting much smarter today, but this is what you need to know. And so you have a couple of general purpose registers, but you have specific purpose registers. So you have the program counter, which is called the instruction pointer on x86, IP. Then you have SP, the stack pointer. And then you have BP, which is less important, but we also like the base pointer. But do you know what the base is?
No, I read about it a little bit, but I
okay.
Don't know.
So it's again very simple. When you create a stack frame for a function, so I'm not talking about the whole stack, I'm talking about the frame of the function you're running. When a function is called, it creates a stack frame. One end of the frame is the base, and the other end is the stack pointer.
Mhm.
On x86 and on ARM2, by the way, stacks grow downwards. This means that the base address is the highest address, and the stack pointer decrements towards the bottom. So setting up the stack means giving the stack pointer the lowest value of the stack.
Yeah, that makes sense.
So you have to do that in assembly before calling main. So there you go.
That is what we do in start as well. So you have the stack frame pointer.
No. What I call a stack frame is the memory used for a single function. What I call the stack pointer is the register that contains the address of the stack, where it is currently, and the base pointer is also a register. So one thing you may want to know, you can write things like this. This here is an address. Like there is no dollar symbol to say that it's an immediate value. There is no percent symbol to say that it's a register. So by exclusion, it's an address. And the linker will find which address because it knows stack from another file. So here you move the address of stack into ESP. Now I said something wrong earlier. I said that you should set the stack pointer to be the lowest address. That's not true. It should be the highest address because again the stack grows downward.
Yeah, so you start at the highest address. And then...
So here what I did is just actually set the lowest address in the stack pointer, so this is not going to work. I need to add the stack size to that.
Okay, which is... But I'm not sure if this works. This should work.
No, this doesn't work. No. You are addressing a register. So register plus size makes no sense. You may have written, for example, stack plus stack size, but then you would have added stack size to the address of the stack, you see? And this means that then, well, actually it might work, because this is what you want, right? It might work. You could write it this way, maybe. No, not this way. You cannot add to your operand. This is your destination. What's the meaning of it?
So you're moving...
Yes?
You're moving stack pointer to the address of stack.
No, it's the reverse. It's from left to right.
Okay.
You move the address of the stack to the stack pointer.
Okay.
So you might try stack plus stack size on the left, though. Yeah, it should work. Okay, when you want to test your code, you can make an infinite loop by writing jump dot and compile and test, and check the registers in QEMU.
Operand mismatch for compare.
Operand type mismatch. Let's see. Yes, because like I said, we have to reverse the order.
Oh, right. Yeah. Oh yeah. Invalid operand.
What? Oh, okay. So let's see. One second. We could do this. We could try that. Whoops. But then we would write an immediate value. Let's see. You can test that. Let's see if it works. Doesn't work either. Invalid operands. Line 23. Okay. So yeah, if it doesn't work, like Faki said, we're going to do that. That only. Let's check that it works. Stack size. Oh. Okay, so the assembler file works, so we'll have to add the size after. And actually, I'll show you a way that you can do it in a single instruction, but we'll have both because this way you learn both ways to do it. Yeah, we have to fix that. We have no inclusion path. I can have that here actually. Whoa, wait. Oh yes, that's right. It's your vim. Oh, that's right. Oh, this is going to be annoying. Yeah, okay, let's do it anyway. Oh, yes, it's this. No, it's not. I'm looking for, yes, this option, print file name include. And the reason it's done this way, this is like, this will have to be explained because it's really tricky. Basically, GCC is not compliant, is not fully compliant. And wait, what happened here? It's not fully compliant in that if you don't have this option, you don't have the headers that are mandated by the C specification by default in freestanding mode. So for example, let's take a look at this option. Print file name include GCC. Sorry. It gives you the path of the internal includes, those of the compiler. So you're going to find all the includes that come with the compiler really, and not with the C library, for example, and you're going to find this one here. And like these ones, which are C11.2, the arguments, because obviously the C library may not know about variable argument functions. Bool, standard definitions, this gives you null, by the way, and offset off, so it's kind of important. So yeah, I'll have to explain that. Definitely. Warning, linker input file, wait. We changed that, right? Oh, CPP flags, but it is used. That's weird. We don't have a, yes, we have a CC variable. It's probably because I need to write this. Right, yes, okay. Done. What is necessary to make X15 a KVM hypervisor? I'm not sure. Oh, you told me already. Sorry, Lori Master, such a bad memory.
Okay. And then we're trying it out with the object dump, right?
Or you can run the virtual machine and see what it does.
Oh.
We have a virtual machine, let's use it. Okay, what you can do now, for example, is look. Yeah, you can look at the ESP. So it's obviously wrong, and I think the reason it's wrong is because so disclaimer: I am not an assembly kung fu master. Okay, and especially this syntax, which is rightfully called confusing. So lots of trial and error. I suppose what we should do, like what happens here, is that we're actually moving the value at the address of stack into ESP. We move from memory to register. What we want to do is move immediate, so the address actually, like that should work, and then we should have it. Right? Yes, we have something that looks like the address of the stack. We can check that by using nm. nm means names. See?
Okay.
So yeah, this is good, but we only have the beginning of the stack. So what we could do now, I'm going to test that. I think I needed a parenthesis, but yes, that makes no sense. Now that I understand how the symbol works. Doesn't work either. So we have to manually add. That's your job now. To use the add instruction to update the stack pointer by incrementing it with the stack size.
Wait, this is not where the one. Okay.
So be careful. We use AT&T syntax, which means the order of operands are reversed compared to what's in the specification.
Oh, also, is it not that we're missing stack size because it's in?
Yes.
Can we do include here?
Yes.
Or
That's why we use an uppercase S.
okay, gotcha. Could you give me one of the brackets? Oh, there we go. But now this is adding.
Not bad.
Okay.
So we have a stack, which means that now you can call a C function. And you can call main, basically. Main already has an infinite loop. So we have a couple of ways to call a function. There is actually a call instruction in x86, which is basically a push with the return address plus a jump. But since we're not going to return here, and we don't pass any argument, and we don't expect anything in return, we can use jump directly.
So after this, we
Well,
jump to main.
yes, or you replace the jump that you already have, but it's up to you.
With the test. Yeah. And this would get us there. How do you wait? That's with GDB, isn't it?
You can use GDB, yes. But if you use GDB, you want the virtual machine to keep running.
Oh.
So wait, I'm gonna help you with that. Let's put that in the background. And so yeah, you can use GDB on the kernel. So by doing that, by loading a file with GDB, you let GDB know about the symbols, the sections, all the information that is contained in it. the same way QEMU and grub actually loads your ELF file into memory. So GDB knows about your symbols. Then you need to connect. So I think you can do that. Okay. And now you know where you are. You can also print the registers the same way. So we have that value. That's good. The check passed. We have the instruction pointer, which matches the 8th line of main.c, so we are in the infinite loop in here. You can list the code, and you can disassemble it. Okay, so it's 11 p.m. What could we do quickly? I guess we could try writing a letter on the screen. So I'm going to do something very ugly. We're not going to keep that. Wait, we can commit your code right now, okay? Because that part is done. Let's say it's good, it's done. We're going to commit it.
Would you like to add the ignore file for that as well? Then?
No, not yet.
Later?
Yeah, later.
Okay.
You can actually use git commit -a so that everything that is modified but not staged is also committed.
-a?
Yeah. It's not really enough. You did two things. Oh wait, did you? Actually, let's have a diff. Oh yes, some of it is also added. So we added a couple of things. Oh yes, the make file was not entirely added. That's weird.
Yeah, the
okay.
first commit was the make file, as in when we set it up.
No, that's not what I mean. I mean, it's part of the change here. So that's what C8 was telling me earlier, that everything was not committed. Because you see, we shouldn't see that. It's not part of the changes normally, but apparently they are. Like, why? That's weird.
But you did change them, though, right? I'm not sure what you're...
I mean, I think things that I thought were committed were not. No, git add, well, no, you can. Git add just tells git, I'm answering SOWAFL by the way. Git add just says that a file is now staged. So if it was not known by git, it becomes known and staged. And if it was known but not staged, basically here, modified, not staged for commit, if you use git add, it becomes staged for commit. Git add adds to the staging index. And what I mean is that this shouldn't be here. It should be in that commit here. See, it's in here. So maybe, no, I used that wrong. Okay, that's how it should be used. Okay, that makes more sense. Now we have all the changes that were made. So we did two things. We added a check for the bootloader, and we set up the stack. So that's what you have to say. And one thing, you have some red here. I'm personally very, very picky about that. Done. You basically had an empty line with space at the end. I felt compelled to remove it.
Okay. I've basically gotten into the habit because at certain times you need that empty space.
What you really need is an empty line, a new line. This is actually specified by POSIX. Like you can actually find POSIX saying you need your files, your text files, to end by or with an empty line. A new line character, exactly. And really, it's not the stack. It's really set up the stack, set up a stack, because we're gonna have a couple of them.
There. That's good.
Yeah, sure.
And then this pushes it to
Yeah, it should work like this.
my thing, and then
The reason why it works without doing anything is because we created master. Well, master is automatically created to track the remote master branch in both ways, pulling and pushing.
Yep.
Okay, so that's good. I'm gonna switch back to reload, but that doesn't really matter. To my own repository. Well, actually, you can make the pull request. Let's do that. You know.
Do you have the command for that in code, or is that something you
No,
do?
on GitHub. There is no command really for that. It's usually done by mail.
Okay.
Although there is a git send email command, but there is no point here. We're using GitHub for a reason. So, oh yes, you can do that on your own machine. Are you doing that on your desktop right now?
Yeah. Yeah.
Okay. So I'm gonna close this. Close that too. Go back to my repository, which does not have any of the changes we made. Now, guys, what could we do in like half an hour if Metal Snake also has time? Do you have time?
I have time.
Okay.
Yep.
What could we, yeah, I said we could print something on the screen. Like it's not going to be, you know, very clean. We're going to write a true driver for that. But I think that's something, you know, it's very easy. It's going to give us some output, something to play with, and actually see, you know, happening besides register. Print a short message to the screen. Yeah, we can do that. Yeah, a hello world, exactly. We're going to do that.
Okay. I've made the pull request.
And it's not updated automatically.
Yep. I think that should be.
Why do I need to write a comment?
Yeah, I had the same thing. I'm not sure why.
But do I need to write a comment?
No, I didn't provide one. So... Oh, okay.
So is it actually merged? I guess it is. It is merged. Okay. So yeah, as you can guess, I don't use GitHub much.
Yeah.
Let's go. We'll watch recording tomorrow. Thanks for the stream. Great work. Thanks for watching. And yeah, thanks for your enthusiasm, by the way. Back in your boot S, you have a stray JNZ. It's not a stray. What do you call it, a stray?
After the check.
Oh, wait. Oh, that's right. That's right. I have three. We have three repositories actually. So yeah, like you, I have fetched from GitHub, and I'm going to update my master branch from GitHub master. Okay, good. So let's see what WoxoWaffle is saying. We have a stray JNZ. Is that supposed to check if something is messed up? Yes. I call it a stray because I'm not sure about what it does. So here we have a compare. Compare works by subtracting its operands, and depending on the result, it's going to set status flags. Especially like if the values are equal, the result of the subtraction is 0, and so the z flag is set. So this is a conditional jump, a conditional branch, which says jump if not 0. So basically, if the value in the AX register is not the magic we use to check that we have been booted by a multi-boot compliant bootloader, we jump to this address, which is the beginning. So yeah, I have to explain that, but the right way, well, it's not the right way, there are multiple ways to do it, but a very common and good way to do it is to add a comment for each line in assembly. I'm usually against, like I say it often, I'm usually against spamming commands. Comments are, like, they can quickly become noise. They're not checked by anything else than humans, so we make mistakes. Comments are bound to be full of mistakes at some point if you have too many of them. But in assembly, where you have, like, the language doesn't really make it easy for you to make the code explicit, self-explanatory. Having a comment per line is actually good practice if the line is not obvious enough. And here, like, yeah, maybe it's obvious enough, but again, it's an educational kernel, so I'm definitely commenting that at some point. Not now, I'm doing it on stream, but it will be written in the file at some point quickly. Whelp, hehe. So yeah, basically it's an infinite loop if if we were not booted by a multi-boot bootloader. Sorry if you already talked about it, but do both of you plan to do this regularly on stream? Yes. Or that was a one-shot thing to sort of introduce the workflow and then everything is done after? No. Everything is done on stream together. So it's going to take time, a couple of weeks, maybe a month. We'll see, but yes, it's not just booting. It's also there's a couple of other things that we're going to do, especially scheduling. It's probably going to be the most interesting thing. Like, so yeah, implementing threads, implementing mutexes, handling interrupts, really the basics, but the basics that you really need to know and understand. And it's also very valuable in user space, because when you understand interrupts, basically you understand signals. When you understand that signals are actually like interrupts in user space, you understand why you might have deadlock if you call functions that were not meant to run inside signal handlers, and you understand what async signal safety means. Because I agree that when you read something like this, signal safety, it's really not obvious. Like, what does async signal safe mean, you know? But when you understand why interrupts are so restricted, and when you understand that signals are actually implemented almost like interrupts, then you have a very good idea. So we're gonna see all that. Okay, we have code. I'm gonna add here that it's not reached. And just in case, I'm going to add an infinite loop in case we forget. Not much to say about that. I already said it all. And in main, let's actually write a hello world. So we're going to have a function that we're going to name print, and we're going to have data. Actually, we already have data with the stack here. Okay, I'm going to make the function static. So what I need to know is how to communicate with the hardware that is going to print. And that hardware is the CGA console or the VGA console. VGA supports CGA, which supports earlier standards. CGA is basically So it's 16 bits cells. 8 bits are used for the, how could I say, like the color, the foreground color, the background color, whether it blinks or not. So attributes. And then you have 8 bits for the actual character.
Okay.
So that's the first thing. The next thing is how to communicate with it. So you have several ways to communicate with devices. The most common is memory mapped. So let's go find the memory map again. Let's take a look at the images. Yeah, it's actually not bad. But this contains multiple areas. But it's not bad. So you remember our memory, we had the 640K here, and then we have 1 megabyte, and above it we have memory. Oh yes, I forgot about the optional ISA hole. Let's completely ignore that. Let's say it doesn't exist. Yeah, that's those compatibility memory. That's right. And so inside that range from 640K up to 1 megabyte, you have this area. And basically you have BIOS stuff in it. But at some specific addresses, especially this one, you have the video area, which is basically CGA, VGA, etc. And that's where I'm going to write. Now, to find those addresses, unfortunately, it's not easy because the PC standard is not, like, you don't have nice documentation to tell you everything. You have to find it. Upper memory, no, that's not it. Video BIOS, okay. Okay, that's it. VGA display memory. That's not the address I remember. This is VGA, so it's probably really graphic. What I'm looking for is something inside that range, which is text specific, because I want to write text. Yeah, okay. I'm sorry, I can't give you I can't give you how I found it. I have to copy it again. That's the address. And I'm not going to, well, actually, I don't need to take care of lines. It's going to word wrap automatically. You can view, like you can consider the screen as either a vector or a matrix. If it's a matrix, you have columns and lines, like I have here. But if it's a vector, you only have a size, like this. And basically, if it overflows beyond a line, it's going to end up on the following line. So I don't really care about having a matrix. I can just use a vector. So let's set up our video memory. I'm going to use a pointer. I'm going to make it volatile because I want the compiler to actually generate instructions to that memory. It's 16 bits, right? Let's call it video. Okay. It's not going to be very clean, right? We'll make a real driver some other time, and video has volatile this address. I'll make a macro right away. Okay. Now I'm only going to write one character, and again I forgot. I always have to open that for references. What's the foreground color? This is it. Okay, that's the byte we want. In addition to the letter itself, the character itself. Okay guys, time for me to go to bed. Yeah, it's getting late. Have a good stream. Thanks. See you. So, video. Here we're also going to talk about something else, which is NDNS. Because we have 16 bits, but how do I write them? Right? Let's write an A, and I have to shift that. So about syntax here, when I write this, simple quote, some letter, simple quote, what happens is that the compiler is going to generate a char integer, so an integer that fits on 8 bits, because even if char is not specified as 8 bits, everything requires char to be 8 bits, like POSIX, which is the Unix specification, mandates that char is 8 bits. Be careful that with C, char may be either signed or unsigned. It's implementation defined. So, like, signed char is not the same type as char, which is not the same type as unsigned char. They're different, all three. It's really an exception. All of the types are either signed or unsigned and signed by default. So this is basically an 8 bits integer. And this too. But this one is shifted 8 bits on the left to give a 16 bits value. Okay. Now the problem is, should 7 be shifted or A be shifted? And I'll be honest, I don't know. I tried, I saw it worked. Because again, the specification is not easy to find, and the resources on this are not good usually. So let's try, let's see how it goes. Oh, got it right the first time, too bad. Yeah. So you see there is a cursor, and the cursor does not move. If you want the cursor to move, you have to tell your hardware to move the cursor. It's not automatic. So now what we can do with this is we're going to consume all the characters of the given string until we find a 0, which is the null terminating byte. So basically, while s is different from null, sorry, not null, from 0, that's important. We're going to write this. Okay. Now, I'm not making any check on the size, which means that if you give me a message which is very large, it will overflow video memory and write potentially elsewhere. So careful with that. No, that doesn't work. I made a mistake, obviously. Oh yes, silly me. I'm not upgrading the video pointer. That's better. Increase video, yeah. I make lots of mistakes like this. Now, why do I have a small h? That's weird, isn't it?
Yeah, that's a little bit weird. Because the did not translate to.
Yeah, by the way, the strings command is actually also part of binutils.
Okay.
I should use grep instead of doing this. Yeah, it's the correct H. Why does it do that? That's really weird. Really weird. So what we can do is like use our standard infinite loop homemade breakpoint because it's early. Yeah, okay, it's a warning saying it's misleading, which it is. And we'll have an H. And now we can connect with GDB. Whoa, what's happening? I made a mistake. Okay, target remote. Uh-huh. Internal errors with a core file. What am I getting wrong here? That's good. We're using the same script, right? Like here. Yeah, it does listen on the right port. I'm really not sure what goes wrong. It might be a true GDB bug, unfortunately.
In the QEMU script, you're giving it M64. What is that?
Oh, it's the machine. It basically says that QEMU should emulate a 64-bit processor, but 64-bit processors are also like they implement everything that's needed to run 32 bits, 16 bits, and even 8 bits programs. So it's really not a problem. Now we could restrict this. Yes, we could restrict that, but it won't change anything really. Like if it does, I'll be surprised. Yeah. I never tried to write own print function. Well, this is just a small print. If you look at all the code, like we're going to implement. Actually, no, we're not going to implement printf, but we're going to use code that does inside the kernel because we really need printf. It's too useful not to be used. And yeah, we'll have to agree on what we use and what we redo ourselves. By the way, because we're going to need like it's like when you learn a new language. Usually, you don't only have the language; you have a development kit with it, and you have at least standard data structures like linked lists. That alone would be very useful. And yeah, printf, definitely. But we'll have to decide what we allow ourselves to reuse and not reuse. So
Yep.
unfortunately, I can't attach there. That's really annoying. What we could do is check the assembly. So this is the video address. This is 0x7 and 48. And 48 is an upper H. And so this 16-bit value is moved to that memory, and then we have an infinite loop. So it's exactly what I want, and somehow we don't get that. It could be a QEMU bug, but yes, it's quite weird. On X15, I think I cleared the screen at the beginning, so maybe that has an effect. I don't know, but it's basically that. So you understand the principle that you have a pointer here. unlike what you may be used to, we don't give it the address of another variable, we give it a raw address. And that's really how you drive devices when you write code in a microcontroller, for example. Except you don't do it yourself. Usually you have headers provided by the constructor with all these addresses wrapped into like structures or macros that you reuse.
Yeah. Yeah.
So here we do it ourselves, and yeah, basically that's it. Now if we do that, we should have a different code, yeah, quite larger, because we have a loop now. And we have this instruction here, which is what I wanted to show you earlier. Is there 0x20 in that memory slot before you start? Yes, you're right. No, are you right? Yes, that makes no sense. You're completely right. That's why. Much better. Thanks, Fiery Drake. I
Where would
wrote,
they be?
so my mistake was this, because when I wrote the code, I was thinking about this one, and I forgot to remove it here.
Yep.
As usual, lots of small mistakes.
And the X20 is just some random.
Oh, yeah, it was probably there already because it's a space, I think. So 0x20 is 32, if I'm right. The space.
Yeah. Okay.
So Grub cleared the screen for us, and I ORed it with the value we had. And it's not a problem with the others because, actually, if you look at it, I this is always so funny. I use the trick somewhere here, like this. This is how I go from uppercase to a lowercase. I'm going to sleep soon. Okay, Zilpai. Sure thing. Me too, actually. Well, not that soon, but... So I tried doing that myself, and it's a pain if you don't know what you're doing. Obviously. I still don't know what I'm doing. You will. Keep doing it, and you will in time. Alright, so yeah, much better. So I wanted to commit that first. Let's take a look at the differences. I remove that. I add this. Then we have the print function. Okay. So we're not going to do something really clean with the history, okay? But we should at least try to make commits as not as atomic as possible, but mostly atomic. Which means that basically we have a commit that does one thing. And those things on the side are like should be minor. Let's call it on VGA. Or on the VGA screen, or output, or device. Something like this. Okay, so one last thing I wanted to show before we stop. Here in assembly, we have those two instructions, and if you remember, I told you there was a way to merge them into a single. With something that is not portable, it's specific to the x86, but it's a good thing to know too. And that thing is load effective address. So it took me quite a bit of time to understand this thing, but actually it's very simple. Load effective address is basically like MOV, except that instead of storing your operand, it stores the address of your operand. So it's basically the address operator of C, if you see what I mean. And what's nice with it is that you can use modifiers to change the effective address. And yeah, now I agree that this is not the best. This specification may not be the best for students. It might be too formal and too difficult to read. But you can actually modify your destination. Like, let's take a look at how it's done. See, you can write things like this.
Oh, right. Okay.
Now we use the ADT syntax, so it's not exactly the same. I'm going to keep those two as reference. We don't have, yeah, we do have the preprocessor. So load effective address. But we have the same problem, right? Stack plus stack size. Does that work? Or do we have to write... How is it in AT&T? Okay. So it's EDX plus EDX plus times 4. Okay. So this thing is basically used to make access to member structures, to structure members, easier to write. You have your structure pointer, you have an offset to your object, and then you can scale it like an array. So it would be stack. Now maybe you need a register here. I think you need registers. So stack. So okay, it's not a single instruction because of that, unfortunately. I might have to look at how we actually use that. This is pretty good for people new to ASM. Oh yes, the AMD docs, yes. So ESP, and then we want, like we could use EAX now that we have checked it, and stack size. And we store that in ESP. Expecting scale factor. Okay, so no, not that. Does it work without the scale factor? Is it 1 by default? No. So we probably need to move the stack size to EAX. Okay. I'm going to loop to make sure that we have the right value. And we don't. What did I do wrong here? Yes, this is wrong. Okay, better. So it's actually not it's actually not better. I forgot that you had to use registers here. I think you have to use registers, right? Yeah, you have to use registers. And you can use that too, that's right. This is an offset after the registers. Maybe we could write it this way, actually. Like, let's move the stack here. Well, actually, the add is really is really a much better way to write it. I'm not even sure it can be encoded. Like, this would be load effective address of stack size ESP into ESP. We could write that too. Yeah, works as well. I'm going to keep those two here, just so that you can look at them quickly. Um, although, yeah, let's separate them. So we have those three expressions, well, instructions really, instruction blocks do the same things. So this one obviously is, we're not going to keep it. Which one is better? I think the add one is probably better to keep. Like it's the obvious one, and it's the one that you will be able to use on other architectures as well. Load effective address is not like it. I don't know other processors that have something like this. There probably are, but on ARM, for example, you don't have something like this. So
The
let's
load
keep.
effective address. It loads the address that is of stack size, or
It's so imagine I have that. Okay, we're going to focus on those two instructions. This would be in C something like ESP plus stack size. Okay, and this here would be ESP is the address of ESP plus stack size.
oh, okay.
See, load effective address.
Yeah.
When you see it like this, it becomes obvious.
Yep.
And when you read the Intel documentation, you wonder for several hours, what's the point of this thing? So yeah, we're just staying at the, like remaining at the previous implementation, which is like all good. So I'm going to commit that and push it actually. And yeah, we can stop here. If you guys have questions, want to see things, want to discuss, you too, Metal Snake, by the way, I like your opinion and what you want to do next and when. Well, now is the time. It's 11:40 here, PM. What's the time for you, Metal Snake, by the way? Is it the same?
Yeah, at the same time zone. Yep.
Okay, great. So, late. So, yeah.
Yeah. I'm not sure if this is something we can do. Well, obviously it is something we can do. I've tried to allocate memory dynamically as well by writing your own malloc and stuff.
Yes, we will need to do that, yes.
Okay, that's something I look forward to.
Okay. Dynamic allocation is a huge topic, so it will probably require, like, we're not going to study the whole topic itself, of course, but just discussing about the algorithm we're going to choose is going to take a bit of time.
Yeah.
But don't worry, we'll have plenty of time for that. So you were saying it's not something we could do. Like, what's the frequency you could you could allocate for that? Like, how often do you want to do these streams?
Oh, you mentioned twice a week. That is something I can definitely do.
Okay, great. You tell me when you want to do it next. I'm usually available.
Okay.
But we can discuss that after the stream. Although I suppose people want to know when the next time will
Yeah,
be.
exactly. Yeah, it's hang on. Let me have a look. I could say for certain, at least in the weekend, which, I mean, I'm not sure if that's good for people, but
yeah, I don't know. But if that's what you can do, why not? I mean, many people have told me that they would like to look at the videos anyway. So, and yeah, without the music, actually, they will have the whole of it because I know the music sometimes, you know, Twitch
yeah,
erases some of the audio parts because of it,
yeah, exactly, yeah. Um,
even though I didn't
for me,
understand
it
most of it. Oh, that's sad. But actually, the point is educational again. So if you want to ask stuff, go ahead. Lori Master, I'm pretty pleased, but in my opinion, you should think ahead of time what the objective of the stream are. Yes, I've tried, and maybe even prep the docs beforehand so that the least amount of time is spent searching for stuff and thinking about what to do next. So the problem, Lori Master, is that it's part of the goal. I want Metal Snake to search for it. I want to see how he looks for things, how fast he does it, and yeah, apparently it might be too long. Yeah. The problem is that if we do that kind of preparation before the stream, then it defeats the purpose a bit.
perhaps an alternative is that I do look up documents and stuff and read beforehand, but then uh, give a little summary of what I've been reading into. Maybe.
Maybe, I don't know. It's not easy. I can tell you it's
Yeah.
not easy to do it right. But personally, I don't mind spending the time to search because I think it's important to show people how we search and how we find things. And unfortunately, I've relied on my own kernel much too often. But that's also because the information, yeah, can be too long to find on stream. I agree. It took sometimes it takes hours for just getting a few lines correct. So yeah. Oh, but so therefore sometimes I I don't know. Like for example, the linker script, I thought I knew. I tried and it didn't went like it didn't go as I expected. Sometimes just a mistake. Hello, Grubby. You're a bit late, Grubby. Sorry. Yeah, it sometimes it really takes time to do things right. But I think we have like I'm pretty happy with what we have. This is basically what I expected, and I was afraid that we might have that by 1 a.m. So
Okay. Lovely.
that's
That's a good
that's
thing.
uh, that's good. Yeah. We have
Um,
to decide what to do next time, though. Well, decide maybe not
exactly. Yeah.
decide, but what could we do next time? So you mentioned memory allocation. I think we should focus on printing stuff on the screen. So
Yeah.
basically, a very small CJ driver and printf. And for printf, I'm not going to hide you. I intend to use this. So my own implementation, which is in this library, which you can reuse. Any one of you can reuse. It's covered by the MIT license, and it also does scanf, by the way. It's not complete, but it does a lot of things. It basically supports all these specifiers and modifiers, and it's really compliant and standard, except for those options that like things that are not explicitly supported. You won't have them, but everything else is supported and well supported. It works well. It's tested. It's used in several projects. So we're going to use that because this is the code implementing printf and scanf, right?
Mhm.
We're not going to write that, okay?
No. Okay.
But what we can write is a small driver that, for example, uh, what we just did, we print hello world on the screen. So that's not difficult. That's not too difficult. There are a couple of annoying things, like, for example, going to the next line. So you have to know where you are in your line, and you have to skip the rest in order to go to the new line. You see? This
Mhm.
requires, yeah, this is the tricky stuff. But other than that, we don't care. Updating the cursor, honestly, we don't care. We don't care at all.
Yep. Is that no the carriage return new line? That kind of stuff to go to the next line, or is it because it's
Sorry, I lost you.
so to go to the new line you do carriage return new line, right? Or is it a little more complicated than that?
The again, the video memory is a matrix or a vector.
And it wraps around, yeah.
It doesn't know new line and carriage return.
Okay.
We have
Yeah.
to implement it. We have
Mm-hmm.
to look at the characters that are given and depending on them, either write them um, or insert a new line and even scroll. Because, like I said, if we exceed the size of the video memory, what do? Well, we we remove what was before. So we can use memu, for example, for that.
Okay.
Implement sprintf. That's hard. We better do a driver. Hello, hardcore squirrel. You say it in a way that implies that printf is easy compared to a driver, and that drivers are hard. Actually, drivers are not that hard. Really not. What's hard is writing drivers for hardware which is crappy. Like, if you have a very popular chip which comes in dozens of different models, each with their own quirks, uh, writing a driver for that is hard. But if you are on a microcontroller and you have a very good data sheet and the hardware just works as it's supposed to because it's all well tested, well supported, etc., the driver is going to be very easy, usually. Very, very easy. Whereas printf, have you looked at some of the options? Like,
There's a lot you can put in.
let's take a quick look. Okay. Um, padding. That's not straightforward. Well, it's not that hard either. Justification, including padding. And then you have the ones I really like, such as n. The number of characters written so far is stored into the integer pointed to by the corresponding argument. So basically, you can know how much you have written without having written everything. You pass like the address of a variable, of an integer variable, and printf is going to update your variable with the number of bytes of characters exactly that have been written so far. I mean, seriously, what can like? It's not that hard to implement, but that plus that plus that plus that plus that plus everything, and with all the size modifiers, the length modifiers, or exactly, it's tedious. Surprisingly tricky if you want to support floats. Oh, the floating point support is probably the hardest, I think. The most difficult, I agree. The star is fun too. I don't even remember it. Is it standard? Oh yes, instead of a decimal digit string one may write this, that's right. To specify that the field width is given in the next argument, and I think I do support it. Wait, I'm curious. Yeah, it is. Oh, for scanf, not printf, that's weird. Field width is supported. Oh, I'll have to look at the code. Too late. It's to do with supplying lengths in vars. Okay, yeah, it is standard. We just we just saw. So guys, okay, I guess we can stop the stream now. So next time we're probably going to focus on that, on printf and the video driver. I don't think like would having a shell a nice thing, because my problem is that if we have a shell, we need input, and the keyboard driver is really hell to manage. That's something that we don't want to do. The keyboard driver is far too complicated for something simple. Whereas a UART, a serial driver, is much simpler because you don't handle the console side, you just handle the character exchange. So we'll have to decide that too, I think. The very nice thing about VGA is that you can run that on real hardware and it will work most of the time, unless you have like a legacy-free machine, it will work. So yeah, we'll have to see. Thanks for the stream. It was a fun one. Thanks for being here and watching and helping us with that stupid mistake we made. So yeah, good night, guys. We'll talk about this some other time. It's getting late. I'll keep you updated. So I don't know how though. That's a good question. I guess I'll
Maybe
just. Yes.
maybe you could put something in down below where you
Yeah.
might be currently doing.
I guess I'll do that. Yes.
Oh shit.
Bye, guys. Good night.
Good night. Is there anything you would like to do uh, next time? Because I don't really have a very good idea on the order of things, I guess.